Okay. So what we did, we took this non-homogeneous equation, say equation number 15. What are you doing? So just take this non-homogeneous equation Lu equals to F and replace the non-homogeneous term F by delta. Then a solution U equals to capital F is known as a fundamental solution for L, like for this and for this as well. Now you need to keep one thing in your mind for this non-homogeneous term. If it is any kind of non-homogeneous term, we are just replacing it with a delta function. Then is called the fundamental solution of L and must itself be understood as a distribution solution, that is f comma L dash v is equals to r n f of x L dash v of x dx. Now here I have taken L h with a constant coefficients. I have taken this L with a constant coefficient. So L equals to L dash. So even if I write here L, it does not change its definition. And using the derivative rules, this L dash can be passed to this L. Now here minus 1 to the power m will be coming if it is a mth, it is a differential operator of m degree. Because of that minus 1 to the power m will be coming. And if u equals to f is a solution of this equation number 16, so can we write it? This will be satisfying equation 16. So L of f is delta. So just write minus 1 to the power m integration Rn.
That will be like v of 0, right?
Exactly. So that was the, so the fundamental solution, when we write the distribution solution, then it is a point value, like it is defining from Rn to R. So that is coming to be v of 0. So that was the thing which I wanted to say. It is question number 17. Now the most important thing I would like to mention that I am calling this a fundamental solution of equation number 15 if I add any of general f1 or f2 or f3. So what we have done, we have replaced this non-homogeneous term with the delta function. So can we say that this distribution solution is unique? Like whatever you add for Lu equals to 0, this distribution solution will be solution of that. You just add any non-homogeneous term, this will be a distribution solution of that, because delta is replaced for that non-homogeneous term. So this is not a unique solution. So just let's write, notice that a fundamental solution is not unique. Next, we will talk about the distribution solution as well. Not unique, since we can always add to it any solution of the homogeneous equation L of u equals to 0. Now let us assume that f is a distribution with compact support and form the convolution with f. So u of x equals to f star. Then u is a distribution solution of equation number 15. This equation 15 is basically this, because L of u equals to summation alpha a alpha d alpha f star f, and using the property that when this differential defined on a convolution function, it gives, and for this, because this capital F was fundamental solution of L of u equals to delta, so this d alpha f can be replaced, a alpha d alpha f can be replaced with delta star f, and this is equals to f. So L u equals to f. So then u is a distribution solution of this function. It means, have you noticed one thing? If you are able to find out the solution of this function L u equals to delta, if you are able to find out the solution of this function L u equals to delta, that is known as the fundamental solution. Then using that fundamental solution, we are able to write the solution of the non-homogeneous equation, this, and that is known as a distribution solution, because you can apply this thing. Is it clear, or shall I explain it again?
Um, if you find the solution of LU equals to delta,
Yeah.
then you can find the solution to LU equals to F.
Yeah, using this convolution theorem.
Oh yes, because you get V of zero, right?
Yeah. So that was the proof. We find out the solution of. Now the one property has been used of this non-homogeneous term, that f is a distribution and it has a compact support, and it form a convolution with f. If we are able to write this small f in that way, then u will be f star f of x, and this is, and how, then use a distribution solution of 15, because when as soon as you apply operator L here, so that operator will be applied here. So L of u, and this will be defined in this way, and using the derivative of the convolution, that is derivative of the convolution of two function is derivative of one function with the convolution of the another function, and this is defined as L of f. And since f is a fundamental solution, so L of f equals to delta, and when we are taking the convolution with respect to delta function, then it gives the same function. You may check it. I'm just giving an
Um,
example.
you, you
Yeah.
you just said you just said that the convolution of F with the delta gives you F.
Yeah.
Okay. Yes, yes.
So you, this will be coming like f of y and delta of zero something, and that will be simply f of y. That is simple to check, like property of delta function.
Yes.
This is the Heaviside function.
I always thought that the Heaviside function, the derivative of the Heaviside function was the delta because like it's the derivative is zero, and then like at the point of discontinuity, the slope becomes infinite, right?
I would like to say that that like a Heaviside function is defined as when x is greater than or equals to zero, then it is one, and when x is less than zero, then it is zero. So if you are taking the derivative in the positive coordinate, then it is zero. In the negative coordinate, it is zero. But at x equals to zero, we say that we are unable to define the derivative. In that case, we assume that at zero the derivative is undefined because we are not, so simply we assume that at zero the derivative is infinite, because we are assuming that at zero there is a hole, like the function becomes infinite. So that is the way which I am defining like that. So here I am defining this Heaviside function. So this Heaviside function have 1 when ct plus x is greater than or equals to 0, and 0 when ct plus x is less than 0. And this Heaviside function is 1 when ct plus x is, because augment is now ct minus x and ct plus x, and 0 because this is a wave equation. You may solve this thing and you can check it. So I'm just giving you a draw outline. So this is a wave equation, lu equals to 0. So cannot we write it like del u over del 2u over del t square. Again I am explaining the same thing which I started in the very first three lectures. So del over del t minus c del over del x, and then del u over del t plus c del u over del x. And when c is a constant, this is an advection equation. So what is the characteristic?
Faultless.
Dx over dt
Faultless.
equals to c.
Faultless.
It means the characteristic is x equals to ct plus some constant, some say xi. So x minus ct equals to xi. So this value will be defined as xi when xi is greater than or equals to 0. When if I am taking in this way, it might be possible that we can replace the role of this one can be taken. In that case the characteristic will be x plus ct equals to xi, and then here we will be coming. So this is the background of writing this fundamental solution, but that is not the goal of this topic. So I'm just dropping it and you may go over that, and you already know these things because you are very well aware of the characteristic and how along the characteristic the solution of the wave equation is constant. That's why it is a wave. The information is propagating with a constant speed c, and it is traveling a constant distance c of t at every time step. So it is like this. The same information is propagating with the same speed. So that was the wave equation, and this ct plus x, the idea behind writing this ct plus x is the same, the characteristic. So this thing, how, why it is I am so every time when I am writing the solution of the wave equation, the first thing which should come in your mind will be advection equation, because you guys are very much aware of the advection equation. I don't think you will be able to see this, but there is an exercise which I have written. I think don't think, because my camera is very bad here. So this exercise, you may go over this exercise and may try to prove this exercise. So I'm leaving it, and might be possible that I will drop it in your assignment. What is Camilo? Is it clear to you? You're not saying any words.
Yeah.
Are you okay in the campus?
Yeah.
He got silent for a very long time. So consider the nth order Cauchy problem. Now, you guys are aware of the Cauchy problem for first order differential equation. Now again I am calling here it a Cauchy problem. So just keep in your mind. I am going to explain. Actually, sometimes we write a words and there is a specific meaning of that word, but we don't use that specific meaning. Like every time it is not possible to write the specific meaning of those words. So if you will pay enough attention to those things, then it is very easy. So Cauchy problem, this is the thing. Why I am calling it Cauchy problem? Can anyone explain me? What is the speciality of the Cauchy problem? What is the speciality of the Cauchy problem?
It has to do like with initial uh, conditions, right? Like initial time conditions.
Exactly. So the initial data is smooth enough, then in that case we call the given partial differential equation is a Cauchy problem. If the initial data to solve the partial differential equation is sufficiently smooth, in that case we call it a Cauchy problem. However, if the initial data has one point of discontinuity, then what we call it?
Riemann.
Riemann problem. Now, I would like to point out one thing. So here the L operator, so just take a look and it will change the definition of the equation. So if this L is C del over del S, then it becomes, if this L operator is C del over del X, then what will be the solution of this given differential equation? What will be the name of the partial differential equation? Camilo, Robert.
Transport equation, I think.
Exactly. So if this L is C del over del X, then it is a transport equation. However, if this L is del 2 over del X square, then it is, say C. Then it is heat equation, I think.
Yeah, I think the heat equation.
Yeah. So that's why I call it Cauchy problem, because you change the role of the operator and you will get different kind of, this is the transport equation in one dimension. If we take C1 plus C2 del over del y plus C3 del over del z, then it will be a transport equation in three dimension. That is not basically a valid statement, because if you drop a color pollutant, then you may consider maximum two direction, yeah, x direction, y direction, because z direction is not going to vary. So this will not be, if you are sending information in space, then we are going to talk about the transport equation in three dimension. But if you are talking about the color pollutant which you are dropping on the surface of the river, then it may take only maximum two direction, one the x direction, or it may go in the y direction. But the most important thing about the river, we assume that it flows in a single direction. Is not it? It flow in a single spatial direction. So when we talk about the flow on a river, then we take only x direction. Is it possible that the flow of a river is in two direction?
You mean like the vector flow? It's just
Like a river can flow
the
in two
flow.
direction. It may flow in the
Flow.
opposite direction or in the straight direction, but is it possible that it is flowing in this direction and then it is also flowing in this direction?
No.
No, so that's what when we drop a color pollutant, it may possible that it direction can reverse sometimes with the flow of the air, but it is one dimension. Now, if we take a rod and we start to give, like suppose if you are taking a rod, that is the heat equation, and you start to give the heat at this point, so what happens, the temperature of the rod start to increase from this point, and after sometimes the temperature of the rod becomes uniform. So that's why we also take here it one dimension. It was just a physical observation. You will get to know why we are taking one dimension and why we are taking three dimension, but it was a very basic physical observation. So where L is a differential operator in Rn, we are taking that it is coming from Rn. For one, it will be the uh, color pollutant flow in river. For two, it may be the flow of the information. So with constant coefficient, it means it is a self-adjoint operator. Suppose k of x comma t is a distribution in Rn for each values of t greater than or equals to 0. So this k is continuously, I am just using the below, like I ask you that there is an exercise, you need to prove that exercise, so I am just using the result of that exercise. I will drop that exercise, like you may take a look in your notes, but so this is the exercise you have to solve. I will drop it in your assignment. K is a continuously differentiable in T, and using the previous exercise it will satisfy this given differential operator kt minus L of k equals to 0 as a distribution in Rn for each t greater than 0. As a distribution in Rn means when we are going to take its distribution with respect to any compact support, like there will be a test function v which vanishes on the boundary of the Rn and which is continuously differentiable in the domain Rn, and we may define this. So this is the defined in a sense of the distribution, and k of x comma 0 equals to delta x as a distribution in Rn. Say this is your equation number 20. We shall call k a fundamental solution for the initial value problem. The solution of equation 19 is then given in by the convolution in space variable like this. Now it is worth noting that the distribution k may be used to solve the initial value problem for the non-homogeneous equation, and the solution is given by convolving the t variable as well, like in this way. So using the solution of the homogeneous equation with non-homogeneous initial condition, Just wait up for a minute. So, using the solution of the homogeneous equation with non-homogeneous initial condition to solve the non-homogeneous equation is called the Duhamel's principle. We are going to use this Duhamel's principle in your unit 4. Unit 4 is heat equation. Unit 4 or unit 5. Next, I am coming to, I have dropped these things. You may take a look and study in a deep way. I am just dropping this explanation because you guys are very smart to do this. I am coming to the electrostatics because that is the aim
Heat
of
equation. Yeah. Unit 4 is heat equation.
unit 4th.
4 is heat equation.
Yeah, so we are going to use the Duhamel's principle in unit 4.
Unit 5 is wave equation.
Unit 5 is
Wave equation.
yeah, so unit 4, this just I forgot to announce that as soon as I will be completing this elliptic equation, I will start the heat equation, and I think by October 18 I will be completing the half of the syllabus of heat equation, and I am planning to schedule the next exam on 23 October is Monday, is it? So I am planning to take your next exam on 24th of October because 24th of October I will be in another state, San Luis Potosi. So I will take your exam and I will drop the class of 23, 24 will be exam, and then 25 I will take a class. So 23 of October will be your next exam. So in short, simply we can write the definition of the fundamental solution. And since Laplacian of u equals to f, so using fy equals to Laplacian of u, we can write u of x equals to integration Rn k of x minus y Laplacian of u of y dy whenever u is belonging to c naught infinity Rn. So if omega is a smooth bounded domain in Rn and U is second order continuously differentiable function in omega bar and x belonging to omega, then u of x equals to integration omega k of x minus y Laplacian of u of y dy, where this u is defined as Laplacian of u equals to f, and plus integration del omega u of y del k x minus y over del nu y, like the differentiation of this fundamental solution, the normal derivative of this fundamental solution in y direction, minus k of x minus y del u y over del nu delta sy, because this is a surface integral, so we have changed the domain integral to the surface integral, so we are using the Gauss divergence theorem. So using basically this is the Green's second identity. So the derivative of the normal derivative of the function is defined in y direction and the normal derivative of the function is defined in any direction. Say this is equation number second. Say
To write the u,
sorry.
we what was the idea of writing u?
Sorry.
What was the idea of writing u?
So we are writing the solution of the Poisson equation in the term of the fundamental solution kx minus y. We already know the definition of the fundamental solution, distribution solution of this. So what was the idea? If k is a continuously differentiable function in T and k satisfies this, then we shall call k a fundamental solution for the initial value problem defined by this equation, and it is given in this. Basically this k forms a kernel. We are going to see how it forms a kernel. Basically we are coming towards the Green's kernel now.
Okay.
From where we got the idea of the Green's kernel. So the idea of the Green kernels comes from the idea of the fundamental solution of the Poisson equation. More generally, equation second holds if u belongs to C2 omega intersection C1 omega bar and the integral omega converges. So the proof is written in your notes. You just need to apply the Green's second identity on the function, on the this function, and this is defined in the omega. So when you will be using the Green's second identity, it will simply reduce to this identity, and then you will take a ball and will apply. Just go through the theorem. If you are not understanding the proof, then please let me know tomorrow. The proof is only of 3 lines. I can continue. I just wanted to start electrostatics. That is a very interesting physical life problem. So let me go on the electrostatics. I think you will be able to understand the proof because the proof is very easier and it is written in your notes. I have written each and every step. Since you have done a lot of things on delta function, on the Green's theorem and on the Gauss divergence theorem, then it will be easier for you. If you are not understanding, then please let me know. Actually, this was not the part of your syllabus. Now the part of your syllabus starts now. So if you will take a look in your syllabus, so there are 3 problems. There are 3 examples. The electrostatics, fluid mechanics, and membranes. So for the fluid mechanics, we are simply solving. I think we are simply solving the flow of the electric flow through a wire, but electrostatics is basically, let's explain let me explain the example. Consider the space R3, a single unit charge placed at a point xi equals to r cube is known to induce an electric field. Have you seen that sometimes you take a rough comb, if you take a dry comb and you rub it in your hair, and then it produce some charge on that comb, and when you are bringing that combs to the nearby your pages, and then it flip your page. Have you noticed? So that's what happened. It had some charge, and your body also had some charge. So when you rub, that charge produce some electric field. That charge get get some electric field. So basically that electric field is not but has some gravitational potential. So when you will bring it to the pages or any light thing, it start to attract towards us. So page is a very light thing. So because of that electric field which it has generated after rubbing it on your hair, it start to flip the pages. So every time if you are talking about a charge, it will induce an electric field. And how this electric field is coming, we are going to see that. And it is easy to check that u xi x equals to mod of x minus xi inverse is a potential function for t. Now I am giving you an exercise. Would you please compute del 2 over del x square of u, please? Please compute. This is your u xi x and compute its second derivative, and let me know what is coming.
First derivative will be e, and then the second derivative would be it's just like the divergence, but in one dimension. So it will be just like
Just compute and tell me. I am not agree with you that the first derivative is coming to be, because x minus I to the power minus 1, so minus 2 will be coming in the first derivative. In the second derivative, minus 3 will be coming. I think if you will be computing it, so you will be getting the same thing, only the difference will be of minus sign. Yeah. Sorry, the second. Mm-hmm. Mm-hmm. Yeah, minus. Yeah. So are you getting that thing? Are you getting this thing? Like minus e equals to minus of del 2 over del x square of u. Okay, so you may solve it at your home. Just let me write. So u xi x is a potential function for u, and this e is basically minus of Laplacian of u. Now you have to make one observation. If you define this u xi x mod of x minus xi inverse, then you can write it 1 of modulus of x minus xi. So I say that this xi is a point in R3 that is coming towards the, suppose this is x in space and this is xi, the charge is at this xi and it is coming towards this x. Suppose this charge, this xi is at infinite. Suppose this charge it at infinite, then what will be the potential function for that at infinite? So when this charge is at infinite, in that case the potential function will be x minus infinite, and 1 upon infinite is 0. So this will work as an initial condition. When the charge is at infinite, then the potential function is 0, and when the charge start to come from the infinite towards the point x, and this is defined for that phenomena when the charge is situated at infinite and it start to come towards the point x. So this is the way, this way to express it. So the first observation,
I think the second derivative of that is the delta function.
itself a function.
Delta function, the second derivative of the absolute value.
Mm-hmm.
It's the delta function. Two times the delta function.
3 times delta function? No.
Two times.
No.
The
This will
second
be coming if you will keep minus sign on the second derivative of that. This will be coming like this. That is the Poisson equation basically. So represent the potential energy that a unit charge of the same sign would have if brought from the infinite to the point x. So basically let me explain in the same way which I have written in your notes. So basically what is the first observation? If this is the potential, what is represent the potential energy that a unit charge of the same sign would have if brought from the infinite to the point x? Then the positivity of the potential energy explain the sign convention E equals to minus of Laplacian of U. So this is the way why we are keeping this minus sign so that the electric field will also be positive, because if we are not keeping the minus sign in front of the Laplacian, then electric field will be negative. That is not acceptable. So to make it a sign convention, we are representing this u psi x, the potential energy, and this potential energy used to bring a charge from infinite to the point x. And when it comes near the point x, when it start to come near the point x, an electric field will be generated, and that electric field is the Laplacian of this u. And to maintain the positive sign, because the electric field is going to be positive, to maintain that positive sign, a negative will be placed just in front of that Laplacian. I'm just stopping this class here. It is your homework how we are finding u E with the help of u. It is your homework, just do that, and then tomorrow we can talk about these things. You have two work to do. You have to read this theorem, and you have to find out the Laplacian of u, that is the modulus of x minus xi inverse. And then we can talk about, so this was the electrostatics. So what is the happening in electrostatics? There is a potential energy, and that potential energy is used to bring a charge from the infinite towards the point x. And to maintain that sign convention, we are is defining the electric field E as the minus of Laplacian of u, so that the electric field is also going to be positive. So this is the
But isn't it the electric field is equal to minus the gradient, not the Laplacian, right?
Is it?
Yes.
Even I am confused with the symbol of, just let me.
Yeah. Because E is conservative. So E comes, well, the electric field comes from a potential.
Oh yeah, it is defining as gradient. Let me check. I think I'm making some mistake. So how the third derivative will be coming? Oh, the one will be, yeah, this is the gradient. Now I got it. Even I was making the disputes. This is the gradient. So basically, how I am proceeding, u psi of x, I took the square, and then the modulus will be reduced. So I took this x minus xi to the power minus 2, and then I took the gradient on this, because it becomes easier to apply the gradient on this rather than applying the gradient on the modulus function. This was the way I was proceeding. Like, I did not solve at my place, I just took this example. So this is the way the modulus will be, like the modulus is basically the positive function. So as soon as you will take the square, and now you can apply the gradient. If it is only x is only one dimensional, so 2 u xi del u over del xi will be 2 of modulus of x minus xi. So you may proceed in this way, but you have to do it for 3 dimension. So it will be like del over del x1, del over del x2, del over del x3, and this is also x1, x2, x3. So this is your homework, just solve it, and then we can discuss it tomorrow. Okay.
Yeah, we have to check that the gradient of that u you gave
Yeah.
us is E.
Yeah, say I'm listening to you.
We have to check. We have to check that the gradient of the u you gave us, it's equal to the electric field, right?
Exactly. You have to do that. I haven't checked. Let me tell you very clearly, I haven't checked it, because I am trusting you so that you will be able to do it. So tomorrow I will also check, and tomorrow we will solve some question as well on the Dirichlet problem on the circle, not on the rectangle. So this is the aim, to cover it tomorrow, and most probably by tomorrow night I will upload the notes. Yeah. So, but before that, please go through the notes of fundamental solution and distribution solution in a detailed way, because I have explained each and everything. So it would be literally very easy for all of you to understand those things. Okay. Okay, so bye. See you tomorrow.
Bye.